All right. So up until now, what we have seen is we started off with, survival models, and we saw what kind of models should we fit to best approximate the processes that we observe in real life. And once we have postulated those models and we have our estimates of mortality, we need to see whether our estimates do confirm the relationship that we think is observed in the data set that we have. So sometimes estimates that we calculate using the number of deaths and the exposed to risk that we see as a particular insurance company. You also have the generalized nature of mortality throughout the population. So let us say we sometimes have census data and the death registration data, which will give you life tables like the ones that we have seen ALT 15 for male or let's say for female. So we see we have two separate tables for males and for female, because if we mix them in one, then that is not considered as a homogeneous population. And that would in a way bias our estimates, and that would in a way not be a very good estimate of the mortality rates, because we know for sure that inherently there are differences between the mortality rates of male and female. And the second kind of data that we also sometimes have is from the insurance companies. So that data is submitted to CMI every time, and those tables are actually just, I think someone wants to join. Let me share the link. Right. Yeah. So sometimes we will have data from the census, which is the whole population, and other times we have tables which represent data from a particular insurance company. So most of these insurance companies will submit their data to the CMI, which is Continuous Mortality Investigation. There is also something known as CMIE, which is something else. So this is mostly in respect to UK, and they publish various tables for different kinds of people and for different kinds of insurance policies that people can have. So this is what we have as standard benchmark for the kind of estimates that we think mu should follow. So again, mortality, as we know, varies with respect to different ages, and for different age group we will have different estimates for the same mortality, and we will have our own calculations from the data that we have observed in the past, and we will try to compare them to the kind of tables that we see. And if we see that there is some similarity, then maybe we can use these standardized tables to make yeah, welcome to the lecture. Okay, so we can use this particular data to figure out, if you can mute yourself, Shirans. Yeah, thank you very much. All right. So sometimes what happens is these data will be used by companies to figure out some, let's say, premium calculations or sometimes reserve calculations. So there are these very important financial decisions that companies will have to make on the basis of the information that they get about the mortality. And these estimates can be taken from the standardized tables as well, or you can calculate it for yourself. But it's of course easier to see if we can just take the estimates from the standardized table. But what happens is we don't know whether the standardized table and the kind of experience we have and the kind of policyholders we have, do they correspond to each other very well? Are they consistent with each other? Is the level of mortality for a particular age group same for our business and for that table? So we'll have these questions, and we have the answers, and to figure out how do we test whether these estimates are consistent with each other or not, we will have a look at some 6 or 7 number of tests in which you can check different aspects of the mortality rates that you want to figure out or that you want to use to make further decisions. So the one assumption that I'm going to make here is that I'm looking at a POSVA model. So again, if I'm looking at the POSVA model, I'm looking at the number of deaths that I have, which I represent as capital DX because this is random variable. And this DX, I say that this follows POSVA distribution and with the mean and variance, which will be same, right? So we have already seen that our estimate of mu x is normally uh, so this is normally dx upon exc, right? So what I'm going to do is to figure out my dx, I will just multiply these both so that if I have large enough data, I can approximate this to normal distributions with the mean and the variance as same. Because again, I'm assuming a POSVA distribution or at least a Markov model. So EXC, and this will be multiplied by mu XS. And I will tell you what does this mu XS represent. So again, the variance is also going to be the same. Okay, so up until now, what we have seen is mu X. This represents mortality rate for age X, right? And this is something that we calculate using the formula dx upon exc. But now what happens is you other estimates of mortality rate. Some of them might be from the standard tables and the other might be the graduated rates. And I'll tell you what graduated rates mean in a while. So if I have mu xs, this would mean mu's from standard tables. So by standard tables, I mean life tables like ELT 15, male or female, or something like AM 92. So these sort of tables you will have, and if you take your mortality estimate from those tables, then that will be denoted as mu x with a subscript s, with a superscript s, sorry. And the next kind of mortality rate that you can have a look at is graduated, and that is denoted with a circle in the superscript here. So these are graduated estimates of mu x. Okay, so now the question is, we know the actual mortality rate, and this pink one is normally known as crude estimate. So this is a very good approximation, but again, it is just an approximation. That is why this is known as a crude estimate. And these are from the standard table, and these are graduated ones. Okay, so now the question is, what do we mean when I say that this is my graduated estimate of mu x? So let me just draw a graph here. So I have my age on the x-axis, and I plot my mu x hat on the y-axis. So for each age, I will have some estimate of the mortality. So let us say this is how my graph looks like. So looking at mu x in discrete time for basically each age in person. Okay, so one more thing, why am I looking at mu hat x here? Because I'm considering age nearest definition, and that is why I just have mu hat x. If I would have, let's say, considered age last, then I would have something like mu x plus half or something. So yeah, but here I'm considering in age nearest, so it's easier for me to just write mu with only x in the subscript. So this is what we studied in the previous chapter. But all right, going back to this particular graph, let's say, what does this graph say? This graph just says that as in when people increase in their age, the mortality rate increases as well, and somewhat exponentially. But again, there is some variation. So these what I have here, let me just make those in pink so that, yeah. So these are my crude estimates. And now when I'm talking about my graduated estimates, so not every time I care about what happens to the mortality rate or what is my precise mortality rate at a particular age, right? Sometimes I want to know this in continuous fashion. So I want to know what happens over a time gradually when people progress. So I will have some sort of continuous approximation for these estimates. And there are again various methods by which we can create this line. So here it's a curved. Otherwise, if I would have plotted just a straight line, I could do that using a least squares as well. But again, we can clearly see that that won't fit it well. So I'm just drawing this 0. So this is called the graduated estimate of mu x. So not necessarily for every corresponding crude estimate, you have your graduated estimate. Be sure know that this point and this point can help us figure out what will be the mortality in this particular region. And because in general, because of theoretical reasons as well as practical reasons, we want our mortality rates to be smooth over time. We do not want them to be, going up and going down and going up and going down every single time. Because let us say, for example, if there are three policyholders, one is aged at 51, one is aged at 52, and one is aged at 53. And if my graph says that the mortality rate for a person aged at 51 is higher, and the mortality for the person aged at 52 is a bit lower compared to 51, and then for the 53rd age person, it's again higher. So if you decide your premiums on the basis of the mortality, then your premium would also vary, right? So again, if you see that the mortality rate for a person who is aged at 52 is lower than that of person aged at 51, then you will charge them a bit lower premium than if a person comes to take a policy at age 51. So no person will come at the age 51. They will always wait up until they achieve the age 52 to take out the policy. So again, this is not very convenient. And sometimes even for the marketing purposes, you want these rates to be smooth, as smooth as possible. But again, there can be a discrepancy now, right? So if I make this particular estimates very smooth, then maybe the true nature of my data gets, crushed somewhere. So that shouldn't happen as well. So this is like art, and you will have to compromise on something to basically balance this thing out. So something known as smoothness and something known as adherence to the data. So you do not want your graduated estimates to be showing some another story than the data itself. Smooth, but again, it shouldn't be very less smooth as well. Because let's say if I draw a graph like this. So if I just draw a graph like this, I mean, this is, okay, maybe not like this. So let us say if I try to smooth it in such some manner, but okay, but again, I haven't really smoothened it a lot. So you see there are still some highs and lows, and this is still not smooth, right? So the one definition that you can use from mathematics of defining a smoothness of a curve is maybe if you can differentiate it, for higher times. But again, that is not the kind of definition we would want to have a look at in this case. So we will see how do we check whether the graduated estimates that we have conform and if they are consistent with the kind of crude estimates that we have. So generally it is, generally we will compare these estimates using the chi-square test. So observed will be the ones that we figure out, that we calculate using the crude estimate, and then expected would be the ones that we expect once we assume a particular distribution function for our number of deaths. So now we know that my distribution for the number of deaths is normal with this mean and this variance. I'm going to have a look at dx here. So this will be my observed value. So the observed number of deaths that I have will be just this small dx. But again, so I think in your books, they have again explained this in a bit more lengthy paragraphs, but the gist of it is the same that I have explained to you guys now. Okay, so in just to summarize, there are three main reasons why we want to do graduation. So the process when we figure out graduated estimates of the mortality rate That process is known as graduation. And the reason why we do that is one, to figure out the smooth estimates of the particular rates that we have observed. Second, sometimes we think that if we graduate these rates, if we smoothen them out, then this might remove some sort of sampling errors. So let us say if I want to estimate my mortality rate at age X, then sometimes we will use X plus 1, X minus 1, X plus 2, and X minus 2 to improve our estimate at the age X. And that is what will just help us sometimes to reduce the sampling error. But again, there is a caveat here. So this can only remove any random sampling error that you might have. Because if you have some, let's say, non-random sample error, something like, let's say, if the data that you have collected is not true to its best, or if the model that you have is not appropriate, then the graduation process cannot take care of that. So there is only the random sampling error that this particular graduation method can take care of, nothing else apart from that. So let's see. First of all, so again, there is one more thing that we should discuss is the kind of graduations we can have. So generally, as I have already explained, there is a bit of a trade-off, right, between the smoothness and the adherence to data. So there will be some sort of a trade-off between these two. If you try to have, so let us say if this is how my data looks like. Okay, so let's say if this is how my crude estimates look like, and yeah, and the one thing that I can do is I can create a graph, something like this. So maybe I just have a graph like that, or I can try to, mimic these points very nicely, and then I'll have a graph something like this. So in A and in B, there are two things that are happening. Here, I have tried to smoothen it as much as possible, right? So there is not much difference between each consecutive age and their mortality rates. So sometimes if this happens, you can see here I have, so here if I now use my graduated rate, the mortality rate would be this, but in actual it is something like this. So there is a chance that you will, underestimate them at the older ages. And again, it doesn't show in my graph, but there is a chance that you might overestimate this particular rate at the younger ages. And if this is the case, then this scenario is basically known as overgraduation. So basically, you have smoothened a lot, and this wasn't required. Because now what has happened is that the very nature that the mortality increases a bit more with age is not captured by this particular graph. I mean, this particular graph follows that exponential, but maybe in actual, this is not something like exponential. So this might happen. So if this happens, if you're a good graph, but again, this doesn't conform very well with the data, then you have overgraduation. So here you are paying much more attention to smoothness. But apart from that, if you pay much more attention to just the fact that you capture all the aesthetics of the data, then what might happen is you get a graph like this. Okay, now this is clearly not at all smooth. So this kind of graphs will be known as undergraduated. So if you see the distance between the crude estimates and the graduated rate is much higher when you have overgraduation, and it will be very low if you have undergraduation. And then what we kind of look for is that it should neither be too high and it should neither be too low. So it should be just, precise, and that is how we will try to figure out our tests as well. And we will use chi-square to again just, basically observed minus expected. And we'll see how far the observed values are from the expected values. So observed will be the ones in red and expected will be the ones in green. So again, my aim here is to see if I can use the standardized tables to make financial decisions about, let's say, the premium or the reserve for a company. And what we want to do is we want to check the experience that we have in case of mortality for our company in particular, and we'll see whether the standardized tables approximate to them in a better manner, or are they consistent with one another. So sometimes we will have comparison for our crude rates with the standardized tables. Other times we can have a comparison of them with the graduated mortality rate. So again, the way we perform graduation will be taught for you guys in the next chapter. And this chapter, in this particular chapter, we will assume that we have graduated the rates and we have a list of mortality rates for all of the ages, corresponding age groups, which are graduated, and the crude ones, so that we can just, perform some algebra and compare them. So I think there is some element of compromise that we expect to see. But again, now what we saw here was, in the previous case, we saw that my dx follows such and such distribution. But let's say if I want to compare my crude estimates with not the standardized tables, but the graduated rates, then I will only make one small change here. So what I will get here is, instead of mu xs, I will just have mu x, a circle, to represent the graduated rates. So really not much of a difference between these. So there will be a circle over there. So again, this is for graduated rates, and this is for rates from standardized tables. So yeah, this is what we will observe. So I think, let me just show you guys some example of okay, so yeah, there is something else that we should is, whenever we try to determine these premium rates, what matters much more is whether we underestimate the mortality or whether we overestimate the mortality. But not in every case, both of these will be our concern. Sometimes you only care if you underestimate the mortality, and other times you will only care if you overestimate the mortality. And as we all, I think as we all know, if let's say we're looking at the life insurance cases where a company will incur a loss, if a particular person dies prematurely, right, then we expected them to. So that the number of times where this particular person has paid the premium is very less or is insufficient to cover the claim amount that we might have to compensate to them. So if that is the case, then you should never ever underestimate your mortality. And in the cases of pensions, where a company will have to, basically keep paying annually some amount, you want to hedge against whether a person might live for longer than we expect them to. So you do not want to overestimate the mortality in those particular cases. And now we will have a look at two particular tables. So examples of graduation, as they call it. So if you see here, we have X, which represents the age of people that we observe. It starts at 30 and it ends at 49. So we have 20 age groups that we are looking at. Then this is our, as usual, central exposed to risk. So the number of people who are exposed to the risk of being dead at that particular point in time when they're aged 30. And here dx represents the number of deaths that we have observed. And here mu hat x is the crude estimate that we have calculated using dx upon axc. And now in the rest half of the table, what they have given you is the graduated rates. So again, we will not have a look at in this chapter at least, to how to figure out this graduated rates, because we are going to assume that we know all of these values. And then you figure out your this thing, which is nothing but the value of dx. So if you see, these are not in integers anymore. I mean, you wouldn't expect in real life scenario for a 27.16% to be dead. Shresh, you want to say something?
Sorry to interrupt, ma'am. Can you please explain? Yes, ma'am. Hello.
Yeah, go on.
Yes, ma'am. How did we get the mu naught x column?
Yeah, so we will study that in the next chapter, Shreyans.
Okay, okay.
As of now, I'm assuming that I have these numbers.
Okay, okay.
Okay. Yeah. So then we will just multiply these with these, and we will get some values for our estimated and basically the number of deaths we expect to happen for a particular age, with the assumption that we consider our deaths to follow POSVA model. And if we have more than 20 less in numbers, then we can approximate it to a nice normal distribution as well, with the same mean and the same variance that characterizes the POSVA distribution. So here what they have done is basically they have calculated the standardized deviation. So if you see, this dx here represents the actual number of deaths that we observe, right, in our population. And this minus what you have here is basically the expected number of deaths, and upon the square root of expected number of deaths, which is, so here this represents the mean, and here what we have is the variance. So this is somewhat similar to the chi-square test statistic that you have. So observed minus expected upon expected. So if you square this everything, you will get the same thing. So dx minus this thing, the whole square, upon this thing, which will be your chi-square test statistic. And what you will do is you will add this up for all of these ages. So if you see, sometimes we observe a lesser number of deaths, and sometimes we observe more number of deaths. So at times you will have ZX taking positive values, other times you will have it taking a negative value. And again, as we know that the denominator is always positive, Z being positive and negative denote which one of these is higher. And then you have square values for each of these, which you will use to figure out the chi-square test statistic. Okay, but this was just one example of the kind of graduation that we can have. So in this particular table, what we have done is we have assumed a particular model. So here, if you see, they've given a very nice note. So we are assuming that this is kind of model. So again, I mean, if you put a log here, you see log and e will cancel each other out, and you will be left with mu x. And so this is the kind of two parametric model that we are using. And we have used the method of least squares. So this is again not a very foolproof method, because if you see, we're assuming a linear kind of a model here, which may not always work best. So sometimes all you can do is have a polynomial. So here we have a polynomial of degree 10. That is why we have 11 parameters considering the intercept. And again, this is the kind of model that we have now fitted. And when I'm talking about the method of least squares, it just means that I'm trying to minimize the residues that I have. So if you minimize the square of the residues and you go on to do that optimally, then these are the kind of rates that you will get here. So here again, we have the same kind of a table, but the method that we have used to graduate these rates is different, because the kind of model that we're assuming now is a bit different than the one at least in the graduation A. So now I'm not going to write everything down, but just show you guys various tests that we can conduct to test various other things that we want to check when we try to use the graduated rates to make decisions. So the very first thing is we want our graduated rates to be smooth. So how do you classify whether a particular curve is smooth or not, or whether a particular curve is smooth enough or not? Because same for this particular points, you can have a graph like this. You can also have a graph which is somewhat different than this, or maybe let me just draw it. You can also have a graph which is something just like this. But if you see what is happening in the red graph that I have drawn here, that I'm consistently overestimating the mortality rate. So I mean, we'll see how do we test for these particular kind of anomalies that we can have for our graduated rates. So first of all, when I'm talking about the smooth, in terms of mathematics, we think that, the derivatives for some higher order should exist. But again, that actually also happens if we don't have a smooth enough curve, because the kind of definition we have for smooth in mathematics is not the one that we're looking at least in here. So what we do is we take the first difference, then we take the second difference, and then we take the third difference. So to just give you guys an example, maybe we can have a look at this particular question here. So this is taken from the graduation A, the table that we just saw, the first table, and these are the ages and these are the corresponding mortality rates graduated that we have seen. So what you do is you will subtract 31, you will subtract 30 from 31 and you write it here and you do this, do this, do this, and you do this, you get it. You get these numbers. So this is your first difference. Then again, you will subtract and you get your second difference. And then you will subtract again and you get the third difference. So if we have a look at, this is not precisely taking differentiation, but this is a bit similar to that. So if you see the kind of numbers that we have here are very, very small compared to the actual graduated estimates that we started off with. And if you see, there is not much of a difference. So even if we have, let's say, 001 here, there is no second number, which is like, 00012. So there is not much of a variation in there. And that is what we would expect for, that is what we would expect if we have a very nice, smooth graduation. So again, these are the two criteria that we have. One is that it should be small in magnitude compared with the quantities themselves. So by quantities themselves, they mean these quantities. And obviously the third difference is very small compared to this. And it should be progressing regularly. So there shouldn't be much variation. So these two conditions are nothing but equivalent to saying that my graduated rates should be roughly quadratic. So again, if these two criteria are met, then you will say that, okay, this is a very smooth result and this is good. So now if we have a look at the graduation B table, so here again, we have the estimates and we take the first difference, we take the second difference, and we take the third difference. So now if you see, there is so much of variation in the data, and also these are like, not that far away in numbers, at least from these graduated rates. So we see that these are basically, not as smooth, at least as the numbers that we had in A here. So again, this is, you should always try to remember that we are trying to compare here. And so what we compare is this column with the third difference here. And this is how you will check whether your graduated rates that you have are smooth or not. Okay, so this is all nothing but they have revised hypothesis testing for you guys. So if someone would like to revise it again, you can go through those pages, but I'm going to skip all of those. And we will try to directly see the kind of tests that we can have to check whether the mortality table is consistent with the kind of crude estimates that we have, or whether it is consistent with the graduated rates that we have. So again, here what they have done is just written the distribution of these particular two cases that we can have. And again, they have written here that these are the standardized deviation. So in general, if we assume that we have sufficient number of lives at each age X, so again, I think the very first thing that we all should observe is that this is Z with subscript X. So the very reason that I have X here represents ZX does not correspond to the whole of the table. This is only for a particular individual age. So this is only for a particular individual age at X, right? And generally what you will do is you will sum it up across for all the ages that we observe. So that is what we'll do shortly. Okay, and now once we have enough data, we will try to replace our hypothesis and we'll check whether my Zx follows normal 0, 1 or not, and whether my Zx's at different ages are mutually independent or not. So again, why do I expect this Zx to follow normal 0, 1? Because I have this dx and this is the mean and this is the kind of standard deviation that I have, which is how I normalize, right? So if I assume my dx to follow normal, and if I subtract the mean and divide it by standard deviation, I should get a standard normal distribution. But we will have to check whether this is what we observe or not. Yes, Shreyans.
Yes, I'm so sorry I lost my connection. I have a question for the previous topic in which we were differencing.
Yeah, go on.
So, is it a general practice that we difference 3 times only?
Yes.
Okay.
So again, I mean, so this is actually something that we are doing now, but in practical terms or in practice, when you go, you will never do this because now we know for sure, even before we use a particular method, how smooth we are going to get our estimates to be. So, I mean, nowadays, this is not much in practice, but they have given it here, so I had to cover it. And
Okay.
they have given 3 differences. So yeah, I mean, this is how some mathematicians might have, capped it. So again, I mean, there is a cost associated with how many number of times you difference it. And if you try to difference it less, so I guess this is a balanced amount, 3 times.
Okay, and just for knowledge purpose, like if the
Yeah.
difference is lower when we difference less number of times, like we get 0.100, when we difference 2 times only, then that is better.
Not necessarily, right? Because you want to see whether these are smooth enough. So
And
sometimes you would, sorry, go on.
yes, and if the differences are lower, it means that the process is smooth enough.
Not quite. So difference should be lower in number compared to the actual graduated estimates. You cannot just see whether a number is low enough or not. You have to compare it with some other number. So we will compare our third difference with the graduated rates that we have. Not necessarily on one-to-one basis for each age, but in general, you just have a look and you see that, okay, these are fairly similar or no, these are fairly, lesser in value than the actual graduated rates. So if that is the case, then you can say it is smooth. But again, this is not the only thing. Even if these are less in number, if they are not progressing regularly, then these are not smooth enough. Because again, as we have discussed earlier, we want our mortality rates to be, progressing in a very nice fashion. It shouldn't be that it is more, less, more, less. So it's fluctuating a lot. We don't want that because our premiums, which are defined on the basis of mortality rates, should be actually, some sort of monotonic in
Yes.
nature.
Yes.
Perfect.
Okay, got
Good.
it. Just one confusion, sorry. Uh,
Yeah.
how with what number do we compare the difference number?
We are just going to have a look at that. Shreyans. Yes.
Okay, okay.
I'm just going to discuss that test. Yeah. So these are the 2 kind of assumptions that we think our model should follow. And now we will have a look at the kind of tests that we will have to do to check whether these are consistent or not. So again, even before we start off with our test, there is some assumption that this particular test rests upon. So if I'm talking about the chi-square test, one assumption is that there should be a homogeneous group that I'm looking at. So let us say if you have males and females in the same study, that is not a homogeneous group because we do not expect mortality rates for males and females to be the same at each age. So if you, let's say if you have a heterogeneous group and you try to figure out the mortality estimates, then it will in a way distort the estimate of the variance that you're looking at and in a way invalidate the test. Because if you play around with your variance, then that will affect your test statistic. And that we do not want to happen. And the other times, and the other assumption that we have is that the expected number of deaths that we observe should not be lesser than 5. Why? Because if we have expected number of deaths that come here in the denominator lesser than 5, then for every subsequent lesser number than 5, we will have a very huge change here, and that we do not want. So we want at least a reasonable amount of deaths for each of the ages that we have observed. And if that is not the case, then you can try to group 2 or 3 ages together to at least have 5 number of deaths in each of the expected groups that you're comparing your observed with. And sometimes if you try to group, then it will reduce the sensitivity of our test, because now you won't be able to check it for each age, but only for a group of age. But that is the cost that we have to pay to be precise in our estimates at least. And yeah, so these are the kind of assumptions that we make. And now let us have a look at this particular thing. So what we do is we just subtract expected minus observed, and we square them, and we divide them with the expected. And this is what you have as zx squared, which we have already seen. But this is not everything, right? Zx here represents only for one thing. So we have to sum it up across for all the ages. And what you get is summation of zx squared over all the ages, which we define as x here. Okay, so now once we do this, can someone tell me whether my chi-square is a one-sided test or a two-sided test? What do you guys think?
My guess is one-sided.
Okay, what about others? So yeah, it is actually a one-sided test. And again, I think even before we go there, we should discuss something about the degrees of freedom that we have. So the number of age groups that you will have is equivalent to the number of degrees of freedom that you will have if you're looking at chi-square test statistic and comparing your crude estimates with a particular standardized table. Because in standardized table, you are not estimating any parameter, and we just expect to have as many degrees of freedom as the number of ages that we're looking at. So in the A table that we had a look at, we were looking at 20 ages, and my M over there would just be equal to 20. But for the B table, we saw that we had a nice particular, so for A and B, both of those were, so there were some parameters that we had to estimate in A and B. So that is not what I'm talking about here. I'm talking about the standardized table, tables that you have in your formula booklets. That, then we will only have to look at, whether my test statistic exceeds the critical value or not. And if it does exceed the critical value, like chi-square, then I know that I can reject my null hypothesis, where I assume that the crude estimates are consistent with the standard tables. And again, the number of degrees of freedom that we will have will again depend on the number of ages that we're looking at. Okay, so now if we are looking at the comparison between the crude estimates and the graduated rates, we know we have had to basically estimate certain parameters, right? Let's say 2 in the first case and 11 parameters in the second model. So you will have to subtract that number from the number of ages that we're looking at to get to the degrees of freedom. So this is the only change that you will have if you are looking at standardized tables or the graduated tables. But the way we figure out the test statistic is going to remain the same. Only that instead of mu xs, you will have mu x circle over there. And that's it. So again, here, if we see some sort of a thing here, so again, what we know is if I observe my value of test statistic as very large number, what does it mean? It means that my observed values and my expected values are very far from one another. And we have already seen that that is the case of overgraduation, right? So let me maybe go back. So we saw that if the difference is very, very large, then that is the case of overgraduation. So if you see here, they have mentioned it, right? If the test statistic exceeds the upper 5% point of the relevant chi-square distribution, this indicates a poor fit or overgraduation. And if it is very low, then it might be undergraduation. But again, as you can see, I mean, there is not a very clear construct whether you can claim a particular graduation to be undergraduated, because it will be lesser than, the chi-square test statistic. But again, we don't know how much less it should have to be for it to classify as undergraduated. So there is some sort of not, I mean, it's not much clear, at least that with that thing in mind. But again, now we have, I mean, this is just one of the drawbacks that we have of the chi-square test. And as we know, this is not at all sufficient on its own as a decision criteria to check whether the kind of graduation that we have or the kind of estimates that we have are consistent or not. So there are 3 deficiencies, and let me try to maybe classify them using some nice graphs. So sometimes, let us say we have this particular okay, so let us say if I have this particular graph and I have these as my crude estimates. Okay, so basically these are my crude estimates. And sometimes what I can do is I can just fit my graduated rates, and let us say I fit them something like this. So now if you see, I have clearly overestimated at the younger ages, and I have clearly underestimated at the older ages, right? The mortality rate. But this will not be captured by the chi-square test statistic. Why? Because these large deviations and these small deviations will be offsetted by each other. Because if you see, at this points and at these points, the difference is very large. But again, at these points, the difference is very small. So on an average, you will, I mean, there is a possibility that the statistic will not exceed the critical value, and in which case you will conclude that the graduation is a very, I mean, it is smooth enough and it is, a proper fit and consistent. But as we have seen, there is large deviation and there is small deviation. So we want to look at, whether this is the case or not. So you cannot look at this particular kind of cases using just the chi-square that we have studied. The next thing that can also happen is sometimes, let us say if this is my crude rates, and if this is how I graduate, I mean, this is how my estimates look like for the graduated ones. So again, the difference is very small between observed and expected. But again, I mean, I can clearly see, right, that there is some sort of a bias here. So it is always trying to overestimate the mortality for all of the ages consistently. So that shouldn't be the case. And we'll have a look at a test known as signs test, where we will just check whether the sign is a plus or a minus. And in this case, we will see that, so observed minus expected is always going to be minus, minus, minus everywhere. So it will allow us to check whether there is some sort of a consistent bias in the kind of estimates that I have. And the third one is again just for the cases where, let's say, this is the kind of crudes that we have, and then let's say this is the kind of graph that I make. So now I know that there is some sort of a overestimation and there is some sort of a underestimation going on here in the tails. So not necessarily every single time that is going to be, there are certain consecutive ages for which these particular graduated rates overestimate or underestimate. So these are known as runs or clumps of ages over which it can be biased either up or down. So we want to try to avoid these kind of cases. But again, chi-square does not clearly help us to figure out these kind of things. So as we know, again, not every time we are concerned about, overestimation. Sometimes we also care about the underestimation, at least in the case of a short life mortality. And if you're looking at the annuities, then we do not want to overestimate. So again, I mean, at least if not for each age, at least for the ages where we see a very voluminous transaction for the business. But I think if you can do it for all the ages, then that is just the best. But let us have a look at another test that we can do now. So this will look at the first defect of the chi-square test, which is whether we have very large deviations from the data, which might, be offsetted by one another. So here what we do is, let me just go back to this. Yeah. So now if I'm looking at standardized deviations test. Okay, so again, I expect my z-axis. So always remember what my z-axis is, my zx. So here what I assume in null hypothesis. So here my null hypothesis will be that my z-axis comprise of a random sample. So again, my m here just represents the number of age groups that I observe. Okay, and I basically want to justify that this follows normal 0, 1 distribution. So I assume this is my preconceived notion that my z-axis, which are the standardized deviations, that they follow standard normal distribution. And this is what I want to confirm for. So sometimes what you can do is you can carry out an actual test. So all you can do is you can just carry out a particular, actual minus expected square upon expected, and कौन है सचिन चाचा है क्या उधर सचिन चाचा इंटरनेट बंद हो गया बोलो उनको ऑफिस पे Sorry guys, I guess there was some internet issue. All right, so I'm back. हाँ, चालू हो गया, चालू. All right, so I was talking about the standard normal distribution that we observe. So let us say something like this, and we know that the mean is 0 from a standard normal distribution, right? And the variance is just 1. That is why I have, let's say, 1, 2, something like 3 here, and 1, 2, 3 here. So every time, okay, sorry, minus 1, minus 2, and minus 3. So every time that I observe my values dispersing around this number line, I see that most of my values lie in between this region, right? And very less, at least negligible values I observe 3 standard deviations away from the mean. So these are the kind of terminologies that I'm using now. So again, when I'm talking about 3 standard deviations above the mean, so I am going to count 3 standard deviations above the mean, which represents this particular case. And all the area that I have here is after that particular 3 standard deviations. And this is 3 standard deviations below the mean. But again, now this is how I would expect my data to look like if I plot them, right? So if I were to plot my ZX, I should observe more and more number of ZXs in between here. And at least, I mean, max to max one observation beyond this and this. So again, I do not expect any of the observation to lie in there, because if it does, then it certainly is a kind of outlier. So now to be precise, we know for sure that between -1 and 1, we have 68% of our data. And from here to there, we have this much, and from only 2% from 2 to 3 and -2 to -3. So what you will do now is you will have this kind of number line, and you will plot all the kind of ZXs that you observe, and you will see which of these intervals that they lie in. So now, if we have, let's say, some value of m, these are the number of values that we would expect for each of these intervals. So this many number of estimates you will think and you will want to fall in this -2 and -1 interval. So I think maybe we should just have a look at an example here. So if we see here, we're looking again at the table A, and what we have here is for observed, these are the number of values that we have observed for ZX. So again, whenever I'm talking about observed, I mean by ZX. So you look at all the values that your ZX takes, and let's say if it is in between -0 and 1, you put a 1 here. If it is in between there, and so you go on to do this, and you will get these numbers. And because we were looking at 20 age groups, we multiply each of these values that we expect. So here we had 3.4, and that you multiply by 2, 0.034, so that you multiply by 20 and you get 6.8. And similarly, you get these numbers here. So now if you see the number of expected dates for each of these intervals are 6.8 in this case, that is fine, but this is certainly less than 5, right? So ideally what you should try to do is you should try to group this interval together and maybe group this as well. So you can group this, and this interval. And again, even if you group them, it is still less than 5. So you should be highly critical of any result that such kind of a test is going to give you. But now, once we have the values of observed and the expected, you will go on and just use the chi-square test statistic and carry out a 5% upper tilt test, let's say. So again, if you combine these 2.8 with 0.4 and 0, you get 3.2. And here is 0, 2 plus 4 is just 6. So 6 observed minus expected square upon the expected. And this you will do for all the cases. And this is your value of the test statistic. And now to figure out the degrees of freedom, what do you think will be the degrees of freedom in this case? Anyone? So here I am not looking at each age, right? I have created some sort of intervals here. But I also used my total number of observed, which is 20, to figure out my actual expected, which is why I will have the number of groups that I create, which is 4 minus 1 for equating the total. That is why I only observe 3 degrees of freedom here. and you will have to just use your table booklet to figure out the chi-square value at 5% for 3 degrees, and turns out this is 7.815. So 10.24 is actually more than 7.815. So even if you do not remember, the criteria to classify as significant or not significant, you can use your intuition. So what we are trying to see here is observed minus expected. And we want this number to be very, very less, right? We do not want this number to be a big number. So if this number is bigger than this, then you reject the null hypothesis, which is that these are consistent with one another and that these actually follow normal distribution. So that is something. And not every time, let's say if you are equipped to carry out this actual test, you can just have a look at the overall shape. So maybe you can just plot all the z-axis and you can see the overall shape. But again, that is not very precise estimate. It is like, looking just at the scatter plot or something. So you can have a look at the absolute deviations as well. And now you would want, or let's say 50% of the data to lie within this interval, because that is what happens in the case of standard normal. So you can use a binomial random variable for the numbers that you observe with the parameters m, which is your n here, the total number of ages that you observe, and 0.5 to denote the equal probability of a particular point lying within this interval or outside this interval. So you would expect 50% of m to lie within this interval and 50% of m to lie outside this interval. But now there's again, one more question. So let us say if we observe a particular graph, okay, then there are two possibilities that we can have. So let us say this is my interval where I expect 50% of my data to lie. This is minus 2 by 3 and this is 2 by 3. So if this is the case, if 50% lies here and 50% lies over there, then this is an ideal scenario, right? I can say that this has indeed come from a normal distribution. But if this is not the case, then there are two possibilities that I can have. Either the number of points that I observe here are more than 50%, or these are less than 50%, right? So if we see that we have very less values here. So let us say if I have something like this, okay? So I see basically lesser than 50% values from minus 2 by 3 to 2 by 3. So I know for sure that I do not have most of my z-axis, let me erase this. So yeah, if I have less numbers in here, which is where my z takes a very lower value. So if I have a number, if let's say I have more number of more number of points in here, then I'm basically in a way saying that there are more number of points that take a higher value, right? So my zx takes much, much higher value. So, and that is again the case of overgraduation. Or, also there's one more thing that can happen is sometimes you have duplicates. So when I'm talking about duplicates, it just means that one person has taken out several policies. And we'll look at how to deal if we have duplicates in our modeling in the next chapter again. So we are assuming that we do not have any kind of duplicates. And now the other case could be if you have more than 50% in the smaller range of your Zs. So let us say if this is the case and you have more than 50% in here, then this will be the case of undergraduation. And this is the case of overgraduation. So here you see more number than you expect for your Z, where they take a very, very lesser value in number. So too many small values of your standardized deviations will suggest basically that there is undergraduation and that you have tried to basically fit it very, very close to the data. And that is the reason why you have observed minus expected square as well, very less in number. But again, that is not the kind of test that we're doing here. But I guess if you draw some comparisons, then, because these are not different methods, these are not different in terms of the nature, but different in terms of the techniques. And essentially at the end, the result that they will give you should be the same. So again, sometimes you can clearly say that you have outliers if you observe a value of Z which exceeds, let's say, about 2.5. Or even if it exceeds 3, then you can clearly see that, okay, this is not normal for sure. And another nature of normal distribution is the so-called symmetric, right? So the distribution should be symmetric. So the number of positive z-axis that we have and the number of negative z-axis that we have should be almost similar. It shouldn't be the case that out of 20, we have 19 z-axis which take positive number and only one z-axis which takes negative number. Then we can clearly say that, okay, this is not normal.
Ma'am,
Yes.
actually, I had a doubt in the chi-square test. You said that we always subtract 1, right? So, like, once we see the test and all.
Yeah. And so, okay, so we do not always subtract. Only
So
when we
equate.
When do we subtract? Okay, so I have actually explained this in previous lectures, but just to give you some idea, what happens is when we have these expected numbers, we only know that 34% of the data should lie within this interval, right?
Okay.
So what we do is we observe some ages. So in this particular case, we observed 20 ages, right? So what we do is we multiply that 20 with 34% here to figure out how many number of deaths do I expect. What is the number of ZX that I expect to lie within this particular interval? And because you use that 20 to figure out your expected numbers, you have to subtract 1 degree of freedom from the number of age groups that you have. Perfect. Very good.
Okay. Understood.
All right. So now this is the kind of test that you can do to check whether there is a large deviation in your data or not. But again, this does not overcome the other deficiencies of the chi-square test, which is, do you have a consistent bias, whether you consistently overestimate or whether you consistently underestimate. So now we move forward to another test, which is known as science test. Okay, did we miss something here? No, right? I think I'm not going to show you guys how to do this because I think you guys all know, right, how to figure out this value from your table booklets. If anyone does not, and then you can contact me later. Okay, so now we will have a look at this particular test, which is known as science test. So here we don't care about the absolute numbers. We only care about the signs of my ZX. And what we assume is that roughly half of my z-axis should have positive value and half of my z-axis should have negative value, right? For them to conform to a nice standardized normal distribution that I expect them to follow. But again, now not every time we will have large enough age group to approximate it to a normal. And if that is not the case, then we say that the numbers follow by normal distribution, where M being the total age groups that we look at and half being the probability, so that it is positive, let's say. So we'll have a look at, the groups of the numbers of z-axis that are positive. So half is the probability that we want them to be positive because we expect it to be, fairly distributed among the positive and the negative values. So if you have more number of positives or more number of negatives, then that would suggest in a way that the kind of graduated estimates that you have are biased in nature. So let us try to see how do we do this particular test. So here step 1 is just to count how many graduated rates lie above and below the crude rates. So this is basically just trying to calculate whether, how many number of z-axis do we have as positive and how many of them we have as negative. And then what you will have to do is figure out the probabilities for each of these things. So statistic. So in this particular case, I'm only going to look at the positive numbers. You could equally look at the negative numbers as well. But just to be consistent, I'm just going to look at the positive numbers. And even if you look at the positive numbers, then you know that, the rest of them are negative. So if positive are 50%, then you know for sure that the negative are also 50%, roughly. So, okay. Now remember the hypothesis that we made. We assumed that the number of positive values for z-axis that we have should follow a binomial distribution where m is the total number that we have and half is the probability that you will observe a number to be positive. So here this might be a bit confusing because the number of z-axis that are positive are also denoted by capital P, and when we talk about the probability we use a capital P again. So this is just the probability that the number of z-axis that are positive is equal to some x. Now this is not how, this is generally not the distribution, this is generally not how it looks like. So if we just have a look at this thing, ideally, you would expect this to be mcx times a half raised to x and a half raised to, the negative numbers, which will be m minus x. So if I expect my p to be x, which is just saying that x number of times I see my zx to take a positive value, then half is the probability that it takes positive number raised to x and the probability that it takes a negative number raised to the number of negatives, which will just be the total numbers minus the positive numbers. So this is what you have, and this will cancel each other out and you will be only left with this as the probability. But again, this you do not use every time. This you will only use if you observe the value of m not large or very, very small. So this is the kind of thing that will happen. But again, now here the test statistic can be a bit confusing, but let us see. So here first let me just draw a number line. So let's say if I am trying to draw just give me a minute, guys. Yeah. Okay, so now when I'm talking about this particular test, I know that I can neither have more number of positive deviations and I can neither have more number of negative deviations. So I have to be careful about both the ends. So let us see if this is the ends, then I expect, if I'm looking at 5% test, then I will divide this as 2.5% on both the extremes, right? And here we will be looking at a two-tailed test. So this sign test is actually a two-tailed test and which will just try to figure out the overall bias. So here what we are doing is, so first of all, what does my P being equal to X represent? It just represents the number of positives that I have is equal to some number X here. So when I'm talking about, the number of positives that I have, there is a minimum number of positives that I should have and a maximum number of positives that I can always have. So my number of positives should never exceed a particular number and should never be below a particular number. For it to just be, appropriate to the normal distribution and to basically correspond to the consistency definition that we have defined earlier. So here what we do is we have a look at the smallest value for k. So my k here, so when they're talking about the smallest value of k, this is what we're talking about. So how many number of positives I should have such that the probability that I will observe these particular numbers will be either greater than or equal to this thing or less than or equal to this thing. So we can have a look at this or we can have a look at this as well. So if you use both of these cases, this is the kind of condition that you will get. So you would want your P here to be less than or equal to m minus k and greater than or equal to k always. And you will try to figure out the smallest value of k for which this kind of condition is particularly satisfied. So I think this will become much more clear if we have a look at the example. But again, not every time you should use this test statistic kind of a thing. Sometimes we can also have a look at the p-value. So let us have a look at an example. So again, now what will be the p-value is, I mean, we know the p-value we decide a priori. So let us say we're looking at 5%, and this is what we have defined. And because this is a two-tailed test, the probability that we will calculate, we will have to multiply it with 2. So here let us read the question. A graduation covers 20 age groups. So I know that my M is just 20 and has resulted in 6 positive and 14 negative deviations. So if you just have a look here, we see that, okay, I mean, this is not fairly distributed. And they have just asked us to carry out a science test on these beta values. So there is one thing that we always have to remember. If you observe the number of positives lesser, so let us say if I denote the number of positives by P, if this is lesser than M by 2, then your probability that you will have to compare this thing with is going to be 2 times the probability that this P is less than or equal to some number, which is basically this P here. And if your P is greater than M by 2, so let us say if instead of 6 positive, we have had, let's say if we had 14 positives and 6 negatives, then this particular probability is not what you will look at. You will look at 2 times P, but the probability that your P will be greater than or equal to P. Because here, if you have lesser number of positives, you don't have to concern yourself with the fact that you will observe more number of positives, right? What you are concerned with is this positive a very less number? Is this 6 a very less number? Are 6 number of positive values for Zx very less? Are these enough? And if you have more number of positives, you only have to look at, are these, I mean, do these exceed the number of positives that I should have? So you care about the greater than here and you care about the less than in this particular case. So now because we are looking at the less than, you have 2 pp less than or equal to 6. And to figure out the probability that the number of positives that you observe is less than or equal to 6, how will you do that? You will have to use binomial. And I think we have binomial table in the booklet. But again, that is not for each of these cases. So luckily, if you do have, so yeah, it's on the page 188 and you can see this number is derived from there. And this is what you get as your probability for the deviations being less than or equal to 6. And can someone tell me how should I compare this now? How can I compare this? So my p-value here is 0.1154 and my alpha level, which is my significance level, let's say I am looking at 5% level. So here I observe my p-value to be less than the alpha, which is the significance level. Then how can I conclude? Does anyone remember the criteria? Anyone? So if I have my p-value taking a number which is lesser than my alpha, then I do not have enough evidence to statistically reject the null hypothesis. So basically, we will have to conclude that these rates are not biased in nature. I mean, even though you see we only have 6 positives and 14 negatives, this can still happen due to some random nature, right? This doesn't in a way just signifies that just because these are not 50% distributed, that these are biased. So again, if your p-value, let's say here, was something like 0.06, then you would have claimed that, okay, this is biased in nature and we do not have consistent estimates. But again, this is where you use actual binomial table to figure stuff out. And sometimes if you have M large enough, then you can approximate this to just a normal distribution. So if we go back here, And we see the binomial distribution it follows is m comma half. So the mean here will be m times half, which is m upon 2, and the variance will be m times half times 1 minus half, which is just m upon 4. So your p, if you have large numbers for m, then the number of positives that you have for zx will follow a normal distribution with the mean a half m and the variance 1/4 of m. But again, you will always have to remember that binomial is a discrete distribution, and if you're approximating it to normal, there has to be a continuity correction that we will have to take care of. So again, this will be a two-tailed test. So let us have a look at an example here. Yeah. So again, now we are looking at the graduation B. And here I'm not going to go back and count the number of ZXs, but that is what ideally you should do. And that is how they get to these numbers, that we have 12 positives and we have 8 negative values. So these are the values of ZX. And that is being already, that is already calculated for you guys. So all you need to do is just count the number of positives and the number of negatives that you see. And now here, if you see, my m is 20 and my m by 2 is 10. So the number of positives that I have observed here is 12. So my calculation of p-value, the probability that I look at here has changed from less than or equal to greater than or equal to, right? So here I'm looking at 2 times p, the probability that I will observe the number of positives greater than or equal to 12. And that comes out to be 0.5034. And again, this is way much more greater than 5%. So this is around like 50%. So way much higher than 5%. So again, there's very little evidence of bias because this probability confirms everything. And all we needed was a 5% chance of this thing to happen. So basically, what I'm trying to do here is, let us say if I have this thing, so I want there to be only a 5% chance that I will observe some number here. So there's only a 5% chance that I will observe some number here, which is for the case of greater than, and for the less than, the same thing I do for this particular. So I hope this is clear. But again, here what we had a look at was the overall bias, right? And now what can happen is, let us say sometimes you see positives and sometimes you see negatives. So again, that might offset each other. And again, this is not a very foolproof method. But again, there is just one thing that I think I should say is, let us say if we have more number of positive ZXs, what does that mean? That means that we have more number of ZXs which take a higher and higher value. So sometimes your actual will be greater than the expected, and you might have some sort of undergraduation going on. Suresh, are you trying to raise your hand? Sorry,
Yes, ma'am. I have one question. Ma'am,
yeah.
Can you please explain again key for positive, why if like 12 is greater than 10, so why do we do key probability p is greater than 12 and for 6 p is less than 6?
Okay, again, first of all, let me just say I'm very sorry because I don't know why I'm calling you Shreyesh today, but yeah, all right. So here I have, let's say, a number line. And what I want to look at is, there shouldn't be too many positives, right? And there shouldn't be too few positives as well. So in this particular case, I've already observed 12 positives, right? So now I want to check whether this is consistent with how I should have expected my positives to behave if this were random. And that is what we say will be the case where there is a 50% chance for a particular value of ZX to be positive and to be negative. But again, that doesn't mean that 50% of the values will be positive and 50% of the values will be negative. But on an average, we do expect that 50% of the values will be positive and 50% of the values will be negative, right? But here what we have seen is, we already know that we have observed more than 50% positives. So now we are not concerned about whether the number of positives we have are lesser in number. We are concerned whether this 12 is a big number, whether these 12 positives denote that there is some sort of a bias towards these estimates taking more and more positive number. And that is why you care about this p-value being greater than or equal to 12. So that, because see, you have only observed one estimate, right? You only know that the number of positives that you have observed is 12. But again, this is just one sample size from one particular table that you have observed. But all you need to concern yourselves with is, what is the chance that this 12 could have been, greater than this particular number? And this is what you get here. So this
Okay.
2 times, I hope this makes sense.
Yes, ma'am. Thank you.
All right, very good. So now again, this is another test that we will look at. So fourth test, which is known as cumulative deviations test. Okay, so the science test that we just looked at was a two-tailed test. And the same is going to be true for the cumulative deviations as well. So here, as the name suggests, we are going to not only have a look at one dx, but the accumulation of all of those. So here I'm trying to measure, in essence, the goodness of fit for my data, whether the number of deaths that I see are more or less similar to the number of deaths that I expect to see. So if you see here, again, we are making the same assumptions. So we are looking at the comparison between the crude rates and the graduated rates. And if I look at the deviation, this will have mean as 0 because this is just going to get subtracted, and the variance will remain the same because this is just some constant that I'm trying to subtract. So once this remains the same, and I'm now looking at the value that we will now be comparing is not the one dx. We will compare all of the dx's with all of the expected. So here we look at the summation of the difference over all the ages, and we know that that will follow normal. And why? Because each of the dx we expect to be independent of each other. So you just add them up, and that is what you get here. And the covariances is 0. So that is why you just have a summation over all the ages for this particular case here. And now you will standardize them. So again, you expect them, after standardizing, we expect them to follow normal 0, 1, and not much assumptions. Only one, that the normal approximation is reasonable for all the ages. So again, here you can apply this particular technique for all the age range, or you can do it for a particular range that you are concerned with. So again, that's up to you. And these are the steps. So once you figure out this test statistic, basically this dx will be given to you, these numbers will be given to you, and you just have to figure out this test statistic. And now again, you will just compare this particular thing with the critical value that you have. And if you see that your test statistic takes a very, very higher value, then it would just indicate that your graduated rates are, in a way biased. So maybe if they take a very, so maybe if you're, basically so I think we should try to see an example, and then I think I should explain that to you guys. Okay, so now we will try to apply the cumulative deviations test to the whole range of the graduation age. So this is what I want to do. And we observe these many number of dx and this and this. So again, previously what we used to do is we used to sum up this particular whole fraction for all the ages. But now if you see, we have these summations separately. And there is only one standardization that we're doing. Instead of standardizing it for all the ages, we standardize the cumulated variables over all the ages. And you only get one standardized value, and this will be your test statistic. So again, because we care about the bias, both positive and negative, we are looking at a two-tailed test here again. And again, normals, so that is why instead of 5%, we are going to have a look at 2.5% rates, and that is just plus or minus 1.96 here. And yes, this lies in between these numbers. So we kind of say that there is insufficient evidence to reject the null hypothesis. So we are just in a way saying that the graduated rates that we have are not biased in nature, or at least we do not have enough evidence to say that these are biased in nature. So again, I mean, all of the tests that we are studying are going to, so basically all you need to know is, one, whether the test that we're studying is one tilt or two tilt, and second, what is the purpose of this particular test? Because not every test will allow you to answer each kind of a question. Let us say if you are looking at one-sided test, it will only observe either over graduation or under graduation. And if you're looking at total, it could basically, it is telling you about the overall goodness of it. But again, not every time you care about the overall nature. Sometimes you only care about what is happening with respect to the kind of thing that you want to hedge against. Okay, so sometimes what happens is, if you add all of this up, basically if you try to figure out this standardized value, the value that you get here is 0. And that will happen if you use, the least square method or MLE for the graduation. So this particular process will not be helpful, and you should not apply this test if you observe the value of test statistic as 0. So this is one of the disadvantage, because sometimes more number of positives over a particular age can cancel out, the more number of negatives that you might have for the other ages. So this particular numerator will just become 0 in that particular case. And yeah, so this is not something, this is something that we should be aware of. So if at all you get a value of 0 for the test statistic, we should know that this is not the test that is suitable to check whether my graduated rates are biased or not. Okay, and now when I'm talking about the bias, again, there can be different kinds of biases that I can have. And why is that the case? So again, now, if you look at this particular conclusion paragraph that they have here, this is very, very important. So now, here they're talking about whether, Isha, yeah, you want to say something?
No, ma'am, it got unmuted by mistake.
Okay, yeah, it's all right. So now here we are trying to figure out what happens if my observed test statistic is high. So here we observed a test statistic which was just 1.143, right? It directly fit into our interval, and we could basically say that we cannot reject null. So now let us say if this test hypothesis was 2, then what would have you guys concluded? What do you guys think? If let's say this test statistic was 2, what do you guys think you would conclude? So the way I like to interpret these kind of questions is, I will just have a look at this particular thing. So summation dx minus summation sum expected. I'm just going to write expected here. So I shouldn't even do all of this. So observed minus expected. If again, I'm ignoring the denominator and stuff. So I'm just writing if my observed minus expected takes a very higher value here. So I'm just going to write a greater than 0 here for my reference. This is observed. So I will just have observed is greater than expected. So you see that the expected values that you have are too low, right, than the observed ones. And that happens if your test statistic takes a higher value. So again, I'm not writing it greater than 1.96, but just 0 to just be able to, this is just something that I used to remember and I used to infer about the data. So here, if you see, if the test statistic is positive, then it would just say that the graduated rates are too low. That is what we just saw. And if it is negative, then you will have the opposite sign and you will just conclude that the graduated rates are higher in number compared to the crude estimates that we have. So again, they are just not consistent. And sometimes the reason that your test statistic is high could also be because the variance is higher. And when will your variance be higher? Again, that might happen if we have duplicate policies or if we do not have a homogeneous group of people, because that in a way distorts the variance. So again, we're gonna see that in the next chapter. So this was it about the cumulative deviation test. But again, I mean, not every time again, I mean, so this cumulative deviations test, what this particular test did was to overcome the third deficiency of the chi-square test, which was if we observe a very large number of very small deviations or a very small number of very large deviations. So we can check whether this is the case using cumulative deviations test. Okay, but now the next test that we have is called grouping of signs test. So here what we will see is whether we have, bunches of positives and bunches of negatives. So when I'm talking about a bunch of positive and a bunch of negatives, what I mean to say is, let us say if I expected my ZX to be random in nature, I would expect it to ideally have, positive, negative, positive, positive, negative, negative, positive, and something like that. But if let's say I observe my ZX consistently throughout the ages, positive, 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 negative, positive, 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 then I know that there is something going on. So maybe just to give you guys an example, if you look at the Gompertz, you might have remembered that if I fit a Gompertz model to the mortality, it only approximates better to the middle age and the older aged people, right? Not to the younger ones. So in the younger ones, it would basically either underestimate or overestimate, something like, I don't exactly remember what was the case, but there will be any one of those things happening over there. So if you want to test something like that, then you will have to use grouping of signs test, where now you not only look at, the signs of each individual ZX, but you look at the signs in groups. So ideally, if you would expect there to be, no bias, then you would expect that there is a nice variation between positive and negative. But if there is a bias, then you will see consistently positive values, consistently either negative values. So if you have consistently positive values, then you claim those all the positive values as one group, and then the other group, then the third group. So something like that. And that is what we will test against. So we do not want these groups. We want as minimum grouping as there can be possible. So here, if we see that, there is very fewer runs than expected. So when I'm talking about runs, I mean a run of positives or a run of negatives. So if there are very less runs, then I know that I have overgraduated. And if it kind of frequents between positive and negative and fluctuates a lot, then I know that I'm looking at, undergraduated. So again, this is going to be a one-sided test because we are only worried if we have a lower number of groups. If we have more number of groups, it doesn't matter. All we care about is that there shouldn't be too many less number of groups. Because if we, let's say, only have less number of groups, then we are in a way saying that it takes positive, positive, positive for a longer amount of time consistently. And that is what we want to avoid. So here, we will define our test statistic G as the number of groups of positive ZXs. So here, my G represents the number of groups of positive ZXs. So this is what I want to compare against. So now I will have a look at, so if I want to figure out the probability of this particular test statistic to compare it with, the alpha value or something else, or let's say to figure out the p-value, what will I have to do? I will have to figure out the probability that I will observe one positive group or the probability that I will observe two positive groups. So let me just maybe draw something here. So when I'm talking about, let's say if I have 6 observations, then here I observe one positive group, right? And let us say if I have something like this, then I observe 2 positive groups. Or if I have something like this, then I observe 3 positive groups. So this is how I'm trying to group. And now what I want to figure out is what is the probability that I will observe 2 groups, or what is the probability that I will observe 3 groups, or what is the probability that I will observe 1 group, and how can I do that? So first of all, let me use some more notations. So I'm going to denote by N1 the number of positives that I observe, and N2 the number of negatives that I observe in total. Okay, so here And this is what I have as given. And now I want to figure out how many number of ways I can arrange these things in. So the very first thing, the probability that you will observe so and so groups. So let's say I want to figure out the probability that the number of groups. So again, remember the number of groups I denote by G. So let's say if I'm talking about the probability that the number of groups I will observe is P, will be what? The probability that, P groups are there upon the total possible ways you could have arranged, the positives. So upon total possible ways. So first of all, if we want to figure out the number of ways we can arrange N1 positives and 2 negatives, how can we do that? So this is going to involve a bit of combinatorics, but I think we will intuitively know what we have to do. So let us say I have these M spaces, and for this particular case, my M is just 5. And I want to figure out how many number of ways I can place my positives and negatives here, right? So if I already know that I have N1 number of positives, then I can place my N1 in any of these 5 blanks. So let us say my N1 here is 3. So I can place a positive here, here, and then I can place a positive here. Or I can place a positive here, here, and here. Or I can place it here, here, and here, right? So if I fill up my positives, that will in a way guarantee where my negatives are going to be. So my negatives will have to be in each of these cases. So all I have to do is just figure out the number of ways I can basically write my N1s in the 5 spaces that I have here. So this is N. Oops. So this is N1 here. So the number of possible ways I can do that is nothing but M is the total number of spaces I have, and N1 is the number of things that I have to place in M spaces. So MC N1 is the way I can arrange N1 positives in M, and that will guarantee that I have N2 negatives arranged in there as well. But now the very thing that is a bit convoluted is to figure out this numerator here. The probability that you will precisely observe P number of positive groups. So again, this is saying, so let me just erase all of this first. Yeah. So now what I have to concern myself with is, first I will have to see if I have P positive groups, in how many number of ways I can arrange those P positive groups, and what is the probability that I will observe T positive groups, right? So what is the probability that I will observe 2 positive groups, and that will be multiplied with the probability that I have observed 2 positive groups. Sorry, I think I said the same thing again. So let me just say that again. So I will look at, let me just write it here. So first I will look at the number of ways I can arrange T positive groups. And the second thing that I have a look at is the probability that I have T positive groups. So if I multiply this 2, I will get my numerator here. But now how do I figure this thing out? So if I want to figure out in how many ways I can arrange my positive groups, how can I do that? So let us say this is a negative, negative, negative. So these are the negatives that I have. Okay, these are not the spaces, these are the negatives that I have. And now I want to see where all I can place my positive groups, right? So I have 1 space, 2 space, 3, 4, 5, and 6, right? So the number of negatives that I have plus 1 is the total number of possible places I can have my positive group, right? And how many groups I have? T. So the number of ways you can arrange T positive groups will be N2 plus 1 T. So you have T choices, you have N2 plus 1 choices and T numbers. So let's say if you want to place 3 positive groups, you could either place it here, here, and here. So that will just be, 1, 2, 3, 4, 5, 6. So 6 C3. And that is what you will have for this particular guy. Okay, but now for this guy, how can I classify, the number of positive groups that I will have? So to do that, this is actually a very nice thing that we can do. So let us say I now write all the positives that I see. Okay, so let us say I have 1, 2, 3, 4, 5, 6 positives, and I want to decide how many number of groups that I want, which is T. So let us say my T is just 4 here. So I'm saying that I want 4 groups. Now I know that if I want 4 groups, then the number of bars I have to place here is just 3. So if I place these 3 bars, then I know I will have 1, 2, 3, 4 groups, right? And at each of these bar, I will have to place a negative to separate these positives, right? So what I'm doing is the number of groups that I have is T. And that is why T minus 1 are the number of places you can put negatives in, right? So the number of negatives that you have to put in are T minus 1. And how many places you can put these structures is going to be the number of positives that you have minus 1. So just N1 minus 1. Because you cannot put a brick here, you cannot put a brick here and say that, okay, now I have created more groups. There will still be 1, 2, 3, 4 groups, right? So, it doesn't, now these ends do not really matter much. And that is why this N minus 1 is the total number of ways, the total number of groups that you can put, which will be 1, 2, 3, 4, 5 for 6 positives. And 3 is the number of negatives that you would want to put in between to create exactly T number of positive groups. So 1, 2, 3, 4, and this is the number of positive groups that you see. So now once we have done this, you multiply this and this to get your numerator for your test statistic. So now let me clear this stuff. And this is how your probability of exactly T positive groups is going to look like. And the kind of assumptions that we are making here is no assumption. So again, here we are using, approximation method now. So what you can do is if you have a very high number of age group that you're looking at, let us say if your M is more than 20, then you can have, then you can basically use this normal approximation. So you do not have to calculate, these particular numbers. So all you can do is just substitute in the values for the mean and variance and carry out the test as usual. But if that is not the case, then step 1 will be to determine the sign. And once you have the signs, you will have to, count the number of groups that you have. So I think maybe for this question, we should go back. So I don't know, this is 37. So this should be the yeah. So let us say we have a look at this particular table. And now, if I want to determine the number of positive groups that I have, so I see that this is positive, right? So one group, then I have some negatives. So this is positive, negative, 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 and then all of these are positive, right? So the number of positive groups that I have here is 3. And my N1 will be what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my N1 is 10 and my N2 is also 10. I mean 20 minus 10. I don't have to count all of this. So you have 3 positive groups and this are the numbers for your N1 and N2. And now let's go back, and now I should have remembered that page. Yeah, so now that is just the way you will count the number of groups of positive signs. So in this particular case, your G will just be equal to 3. And then for each of those, you will have to figure this thing out. So here my T is going from 1 to K. So here we have to make sure that we look at the smallest value of K for which this summation exceeds the value of 5%. And now let us have a look at this particular example here. I think so. Here again, you do not always have to carry out the test. You can sometimes, just have a look at the number of deviations that you have and compare that with the critical value. So if, let's say, your critical value, if the number of groups of positive deviations that you have, which is G, if your G is less than or equal to critical value, then you can easily reject the null hypothesis. So this is another way that you can just, in short, do this particular calculations. So here, if you see the number of positive deviations is 6 and the groups are 2. And we want to figure out whether this is biased or not. So now again, if you look at the page 189 of tables, you will see the critical value is just 2 and N1 is 6 and N2 is 14 because 20 minus 6 is just 14. And since we've observed 2 groups of positive deviations, you will see that this is equal to 2 and you reject the null hypothesis at 5% significance level. So yes, and that will just say that there is some evidence of the groupings of the same signs. So our null is that there is, no grouping at least, so there is no bias. Or then you can sometimes use this normal approximation if you have m greater than or equal to 20. So this is just one particular example of a left-tailed test, because what we care about is only a lower value of G, right? We don't care if we have more number of positive groups. The more we have, the better it is for us. But again, not more as in all the alternatives, but it shouldn't be very less in number, because that would represent that there is some grouping and there is some bias going on. So here the conclusion will be just that, if you have too few runs, which that is just going to indicate over graduation. So remember, this particular test is one-tailed test, and we look at whether the probability of the grouping of positives is less than or equal to some number. And if it is lesser, then we will reject the null at whatever significance level it is that we are looking at. So here they have just given one example using the normal. So I think, they have used the graduation A. So we know N1 is 10, N2 is 10, and the critical value. So again, I think you all can have a look at your tables and you will see the critical values. So for 5% level, I think it's 3. And the number of groupings we have is 3, but that is not of concern to us, because here we do not really care about that, at least up until we figure out the test statistic. Then when we are trying to figure out the probability, we care about the probability that you will observe some G which is less than or equal to 3. So you see that you have observed 3 groupings, and with that information you want to check what is the probability that you possibly could have observed, lesser than 3 groupings. And if that is less, then you will reject the null hypothesis. So here you can easily figure out the mean and the variance using the formula and just substituting in the numbers. But one thing we have to remember is that you will have to apply continuity correction here. So again, because we are looking at G less than or equal to 3, we have, I mean, the mean and the variance is given to us. But now when we are trying to approximate it to the normal distribution, which is over a continuous range, I cannot ignore the values between 3 and 4 and 2 and 3, right? So if I'm talking about G being less than or equal to 3, so maybe I should draw. So let us say if you have something like this, 2, 3, and 4, this 3 will measure something from here till here for the normal case. And this 2 will measure something from this, and this 4 will measure something from here to here for the normal case. So whenever I'm talking about G being less than or equal to 3, in continuity correction, I will replace it by 3.5. So this is all I'm talking about, because in discrete, I only care about these particular numbers, but in normal, I care about the numbers in between here. So I have to, in a way, say that my 3 here corresponds to everything from this to this. So now I'm looking at G being less than or equal to 3. So I have from 3.5. And let's say if it were G greater than or equal to 3, then you would have this thing from 2.5. And again, because my G can increase in one value. So because I'm going only from 2 to 3 and then 3 to 4, I have this 1. So the difference, and you divide it by half, which is 0.5 that I've added here. Let's say if this were not the case, if let's say I had 3 here and I had 6 here, and let us say I have 0 here, then the number of interval that this 3 captures is no more from 3.5. This will be 6 minus 3, which is 3, divided by 2, 1.5, and that I will add here. So 4.5. So this would have been 4.5 if my G could only take values 0, 3, 6, and so on and so forth. But that is not the case here. So we only observe integer values. And that is why, I mean, 4 minus 3 is just 1 divided by 2.5. And that is why you only add 0.5 here. So this is just a rule of continuity correction that I think is very intuitive, because again, what you're doing is you're approximating a continuous distribution to a discrete one. So it shouldn't be the case that the probabilities for, I mean, for continuous case, we know the probability that this G will take a particular value 3 is just going to be 0, because we're looking at a continuous graph. But for an interval, this will take some particular value. So again, once you solve this, you have a normal distribution that you're comparing against, so standard normal, and this is the p-value that you will get. And as we see that this is less than 5%, so you will reject the null hypothesis and conclude that there is some evidence of the grouping of the deviations of the same sign. So this is just one more test. So here, actually the kind of distribution that we are using to figure out this probability is known as hypergeometric distribution. I don't think any one of you must have studied that, but yeah, that was just some information, and if someone would like to think more about it. Okay, so this is the last test for today. I mean, again, for this whole chapter, and I hope we can spare 5 minutes. So this is again, a similar test to address again just the limitation of the chi-square distribution in detecting the groups of deviations of the same sign. So here, this test is known as serial correlations test. And again, here we are going to see whether we have a run of positives or whether we have a clump of, deviations of the same sign. And if this is present, then the graduation has the wrong shape. So again, I mean, the rationale here is again the same, because if we see that the graduate mortality curve, is constantly and consistently above the crude rates, then we know that we have kind of, overgraduated in a way. And then you will expect the values of the deviations to be positively correlated. And again, if you see that these oscillate a lot, then you will see that these are negatively correlated, because if you observe a particular higher estimate for mortality for one age, you are more likely to observe a lower expected value for the mortality for the next age. And if that is the case, then you are undergraduating, because you are fluctuating a lot and it is not at all smooth, and maybe you are just trying to, adhere too much to the data. Okay, So here what we will have for null hypothesis. So again, whenever I'm talking about serial correlation test, you would have already guessed that now my test statistic is going to be some sort of a correlation, right? So here I'm looking at correlation between what? So what I will do is, again, for people who might have studied time series, will find this much more intuitive. So what I'm going to do is I'm going to have a look at, a lagged value. So let us say I observe Z1, Z2, Z3, Z4, Z5. So this is all the values that I observe. So my M is just 5, only for the example purposes. So what I do is, then I look at Z2, Z3, Z4. Oops, I shouldn't write it this way. So what I will look at is the correlation of my Z1 with Z2, of Z2 with Z3, Z4, and Z5. So I will have to ignore this particular value here. And that is why in the very first series, you have from 1 to M minus 1. Because if I'm looking at one lag, then for this particular value, I will not have any contemporary value. And here you have from 2 to M. So these two series, you will see if there is any correlation. So this will just tell you whether knowing something about Z1 is going to give you some more information about, the values that you will have for Z2. And again, this is for the lag 1. So this is for the case of lag 1. If let's say I'm looking at lag 2, then instead of Z2, I will have Z3, Z4, and Z5. So I'll have to ignore Z4 as well in that case. And that is why whatever you have here is the lag, usually. All right. And, oh, I forgot to save it. Yeah, yes. So these are the kind of sequences that you now try to want to, basically know if there is any correlation between these sequences or not. And the null hypothesis will be that there is no significant correlation. And as we already know, the value of my correlation is nothing but the covariance upon the square root of standard deviation of the first variable and the standard deviation of the second variable. So this and this, so this Z bar 1 represents the covariance from the mean from the first series, and this Z bar 2 represents the mean from the second series. So this again, this is what you have. So if you see, what's changing here is that we have Zi here, and here we have Zi plus j. So you should always try to see, this is in notation terms, it might just be a bit confusing, but you guys know what we're doing. This is the average of the first series, and this is the average of the second series. And you subtract from the means, and you basically try to figure out the covariance and divide it by the standard deviation of both of these series. And once we do that, this is the actual formula, but you can sometimes say that if your M is large enough, then your average value for this and this guy, because you are hardly ignoring two values of Z-axis, right? So these might sometimes, not be that significant in value. So your Z bar 1 and Z bar 2 could be easily approximated by the Z bar. So single Z bar. And then you can use this particular approximation. And then what you can do is from the denominator, you have this M minus J here. You can pick it up in the numerator so that you get, you can easily see that this is one average and this is another average, where things go from 1 to M minus J, you divide by M minus J. Here things go from 1 to M, and you divide this particular thing by M here. So again, this is just the correlation. So if, this Rj here represents the correlation for jth lag. So if your lag is 1, then you are going to figure out R1, and so on and so forth. So here we do not have the derivation, but we sort of know that my Rj follows normal distribution with mean 0 and variance 1 upon m asymptotically. And under the null hypothesis, where I have assumed that there is no correlation between these two sequences. So now what I will do is I will just try to standardize this. So Rj minus 0 divided by the standard deviation, which is just going to be 1 upon square root of m. So this gives me that my Rj times square root of m follows normal 0, 1. And once I know this, I can test this against the standard normal distribution. And that is exactly what I will try to do. So if you have a very higher value for this test statistic, then it will just indicate that basically whatever you assumed in null hypothesis is not true. So it just shows the tendency that you have cluster of same signs. And I think they have just again summarized all the steps here. And again, we have some sort of a conclusion here, where if you observe that the test statistic is too positive. So again, always, so again here, we are looking at one-tailed test. So you have to remember that. So this is not a two-tailed test, this is a one-tailed test, because we care more about overgraduation. So here, again, if you have a test statistic which is too positive, which means let's say if this is of a very high number, then you would know that the rates are kind of overgraduated. And again, there are, of course, some strengths and weaknesses. So here, if we see that these actually take into account the actual values, but sometimes what happened is because if you take the actual values into consideration, then there's a possibility that positives might cancel the negatives. And then the grouping might not be very powerful. But again, you can have a look at this, not for the whole range, but sometimes you can partition your data and carry out this particular test for that particular portion of your data. So here again, they have just given us a nice example for the graduation A table using lag 1. So these are the values that you want to figure out. And then the value of R1 basically that you get is 0.04. And remember, this is not normal 0.1. You have to standardize it. So you multiply this with the square root of 20, and what you get is 1.97. And remember, one-tailed test, therefore 1.65. And this is way much more higher than 1.65. And that is why you see that, you fail to reject H0. Sorry, you reject H0. And that is why you see that there is some evidence of grouping here of the same signs. And now the next thing that they do is just, so up until now, what we saw was we were trying to compare, using the crude rates. And again, if we want to compare this for the standard tables, then this is just going to be the same thing again and again for all of these distributions. So I think the one thing that we can do maybe is to just try to remember if these are one-tailed or two-tailed distributions, because that is something that people generally make mistakes in. And that is something that is not given to us in the formula booklet. So you have to check what is the purpose of our testing and then determine what kind of a test we should do. So again, this whole chapter was, only about seeing whether the kind of mortality rates that we have are consistent with the ones that we expect them to look like with. That could be either the graduated rates or the standardized tables values. So in the next chapter, we will have a look at how do we actually calculate the graduated rates. And that is much more interesting, I would say. So these are just some mechanical tests that you have to do. But yeah, these are powerful actually. So that's all from my side for today. And so I'm not sure if I'm going to take a class tomorrow.